Okay, hello everyone. I'm Liwei Wang, an assistant professor from Carnegie Mellon University. Since all of you have already finished lunch, let me entertain you. So my topic today is AI-enabled design of engineered material system. And the topic today is really about artificial intelligence. We all know about this, how to use electronics to achieve certain autonomy. But here, I'm going to talk about another topic, which is physical intelligence. We are not the only one who make computers. Nature has its own computer, like this flower. It does not have any electronics, but it can do something automatically. And the reason we want to have this physical intelligence in our material system is because it is easy to control, it requires less energy, and more adaptive and scalable. For example, one topic today we discuss is about how to reduce the energy consumption. If you look at the flower, it does not require you to pay any electricity bill for it, but it can do these things altogether. So this is something we want to achieve. In order to achieve this physical intelligence, we need to care about material architecture and stimuli we have in our system. And if you look at why the nature have this intelligence, it's because million years of evolution, materials architecture stimuli, they come together, they co-evolve together. Nowadays, we have the 4D printing. The material can respond to the stimuli. However, if you look at how we made this system, the material architecture and stimuli, they're disconnected with each other. We either focus on material or we only focus on design the architecture. But if you look at the nature, these factors that interact with each other, their interplay is fundamental. So this is something I want to tackle. I want to co-design everything together. I want to discard the world built between these factors. So that's the goal I want to achieve. So in our labs, we focus on this physical intelligence. As I mentioned earlier, we care about how to co-design material architecture and stimulus. This is definitely difficult. That's why we want to use AI or computational intelligence. And I'm very pragmatic because I don't care about whether it's AI or not. As long as it can solve the problem, that is a good method. So here, for AI, we're actually looking at both machine learning and optimization. So we want to use this to design the physical intelligence. That's the first direction in our lab. And another lab is that if we have enough physical intelligence, we can use it to do computing. We can make a materials computer. That's the second direction. Because we are exploring the synergy between the two, that's why our lab is called the Computational and Physical Intelligence Lab. So today, I'm going to show you some examples we have in the lab. The first one is the mechanical cloaking. We try to design the microstructure to control the deformation, and we are considering the architecture and materials. And we want to move forward to take into account the stimuli. So here, we will talk about how to do shear morphing and how to use it to design soft robots that can move. So all these other intelligent systems we study in our lab, and we're using the design algorithm. I want to first start with this metamaterial. The idea is very simple. Just change the microstructure. You can change the macro scale responses. And our idea is that if we have a building block database, by assembling things in different positions, we can achieve this heterogeneous property distribution. We call it heterogeneous metamaterial system, so we can control the deformation at different regions. But to do that, it's very difficult. So here we decide to combine two methods. For the macro scale, we still use topology optimization because it's more adaptive. It can accommodate different requirements. But in the lower scale, the unit cell is more regular, so we can use the machine learning. For example, we had the latent variable Gaussian process to dealing with those topological categorical variable. We also have this degenerative model to inversely design the structure, but we combine it with the macro scale optimization to design the whole system. So here is one extreme cases. We call it mechanical cloak. Imagine if you have a structure made by this uniform unit cell, when you compress it, you'll have uniform deformation. Now, if I have a hole in the middle, when you compress it, you will see this distortion. So what mechanical cloak try to do is to redesign the microstructure around it, so when you compress it, you cannot feel any difference. So to do that, we combine machine learning and optimization, so we can consider different boundary condition or requirement. For example, this one, if I have a hole in the middle, it will distort the displacement field, but by redesigning it, we can recover the original distribution. And because we are doing optimization, we are not just design using the machine learning, so we can easily accommodate different shapes of the void, as well as we can adaptively change the cloaking region so that it can give you even better performance. For example, in these Mickey Mouse cases, we also design the region of the cloaking. And here, we also can accommodate very complicated cases. We have two holes here. Our result can also easily accommodate this new scenario. It helps us to adjust the limitation of machine learning. So these are some metamaterial design, but we are not very satisfied with it because it does not care about the stimuli. So later we move on to consider stimuli to make the whole system that can move. So here are some representative systems we develop. We go from very simple line networks to very complicated kirigami, surfaces, and solid. And we are considering different stimuli like the heat, light, or magnetic field. And some of them, for example, this one, we use diffusion model, we use neural operator, it's good. But a lot of time we find that for this particular area, we want to combine machine learning with some traditional technique like optimization. So I'm going to discuss the 3 cases that we don't really need to use very heavy machine learning model, but we can achieve very complicated design. So the first task I want to show you here is we want to 3D print the liquid crystal elastomer. By changing the printing parameter, we can control how much it will contract. So here we are looking at a network made by these processing parameters, and we are designing many different entities. The first one is the architecture. We can freely move the nodal location, and we can also design its topology by incorporating topology optimization. And we can also design its actuation. The edges, what are the stimuli you want to actuate it? And for each edges, we also design what would be the 4D printing parameters, including how many paths, what's the printing speed, and printing pressure. And here, we need to use machine learning because we want to capture how manufacturing influences the behavior. But the overall simulation and optimization, we use the traditional technique. So it's a hybrid of both, and we can use backpropagation to get a gradient across all these elements and then co-evolve them together. So here is an example. We can automatically design its topology, material distribution, and manufacturing parameter so that given different stimuli, it can morph into different shapes. We definitely need to match with the real world. So here, this is the simulation we design. This is the real experiment. And this is the experiment without any experimental manufacturing consideration. Because we can consider manufacturing, so our result match well with the experiment. And because we are doing optimization, we are not just doing data-driven design. So here, we can easily accommodate different stimuli. For example, here is the UV line actuation. Now, with this, we actually consider seeing whether machine learning is truly necessary. Can we get other inspiration from the machine learning? So here is another cases. We get inspiration from machine learning, but not directly using machine learning. The inspiration we get from machine learning is that when we train a neural network, we first do a forward propagation, and then we can do backward propagation to get a gradient. Now, we have a lot of simulation model. We can also make them back propagate. For example, I have a kirigami. When I do the kinematic analysis, you can consider it as a neural network doing forward analysis. Then definitely, I can go backward to get a gradient. And I can use this gradient to do optimization. For example, here, I can easily design all different magnetic kirigami that can morph into different shapes in just 1 or 2 minutes, even though I don't use any machine learning techniques. And this also goes to this continuous magnetic soft robots. We want to co-design material, stimuli, and architecture. So under harmonic magnetic actuation, it will move forward. So we can evaluate its performance when we're doing this simulation, and we make simulation differentiable. So we can use automatic differentiation to go backward to calculate the gradient, and then we can simultaneously design all the entities together. So here is one example. I don't want to spoil your appetite, but here is a caterpillar. We want this system to move forward, but I didn't give it any explicit instruction. I only required to do optimization, and it automatically evolved this moving pattern. Given different frictional parameters from very smooth surfaces to very rough surfaces, you can see that the frequency kind of increased, but the magnitude decreased. This matches well what we see in the nature, but I didn't give it any instruction. This is automatically given by the optimization. And we can definitely scale up. For example, here we design a walker. It automatically designs the geometry, material, stimuli all together. So this is very scalable. I guess that's something I want to show today, but I feel that the design is really a multidisciplinary research. So I'm really looking for the collaboration. So for example, the machine learning, optimization, solid mechanics, and UQ, these are the rare areas we are very interested. So we are looking for application in manufacturing, materials, and robotics. With that, I'm happy to answer any questions. Thank you.
Maybe we have time for 2 questions.
case you show,
Yeah.
did you use machine learning or you just do optimization to achieve?
I didn't do machine learning. This one, I just give it the objective function is try to move forward in a given time. And then I will co-design the stimuli, the material distribution, and the geometry, and automatically evolve these things. Yeah. Thank you.
Maybe just one follow-up question. I think there is an interesting part on how you are modeling all the materials versus shape. And when in the morning we were talking about like foundation models and so on. So what role do you see kind of trying to understand the space of all materials that are possible, all properties, and also like all operating conditions? Because that's a huge space to explore.
Right, right. So speaking of the role of fundamental model, here I actually try to do something related to that, because when I design these structures, when I give it different functionality, they will have different combination of geometry, material, and stimuli. And a lot of time, different functionality actually share certain architecture or material, which means that we could probably have a foundational model where you have different design corresponding to different environment or different requirements, and from there you can specify some very promising design, and then you fine-tune it to some very specific scenario. So based on the natural, you can see the evolution is also doing that way. We have certain branches, and then it kind of branch out. So maybe the larger branches form the foundation for the foundational model. Yeah.
Sounds great. Thank you, Liwei.
Yeah.
Let's thank our speaker.